In this video, you will learn what nuclear reactions and radiation are, how to balance nuclear equations, and the basics of nuclear energy, including the controversy surrounding it.
A nuclear reaction is a change in the composition of the nucleus. This can take three forms: fusion, the combining of two nuclei; fission, the splitting of a nucleus; or radioactivity, the emission of particles or rays from a nucleus.
There are three types of particles which a radioactive element may emit. Alpha particles are made up of 2 protons and 2 neutrons. They are very large and very reactive because of their high positive charge, so they won't travel more than a few inches before obtaining an electron. For this reason, they are not very dangerous and have low penetration, so it only takes a piece of paper or human skin to stop them. However, if they get inside the body, they can be extremely harmful.
Beta particles are made up of lone electrons, which are usually emitted from the nucleus when a neutron splits into a proton and an electron. Because of their small size and lower negative charge, which makes them less reactive than alpha particles, beta particles could travel several meters and require a heavy cloth or piece of plastic to be stopped. These particles are also dangerous to living things.
Gamma rays are not a particle. They are electromagnetic waves emitted from the nucleus in its attempt to stabilize. Because they have no mass and no charge, they have an extremely high penetrating ability, requiring several meters of concrete to be stopped. Gamma rays also pose a serious health hazard as they are carcinogens.
Here are some examples of how nuclear reactions work. Here we have the element radium-226 undergoing alpha decay. Radium began with 88 protons and an atomic mass of 226. It has now lost 2 protons and 4 AMUs to the alpha particle. To find the element that fills in the blank, remember that the total atomic number and atomic mass must be equal on each side of the equation. Looking at the atomic number, we need an element with 86 protons, so that when added to the 2 protons of the alpha particle, it will equal the 88 protons it began with. The element must also have an atomic mass of 222, so that when it is added to the 4 AMU of the alpha particle, it will equal the original 226 AMU. So the element we are looking for is radon-222.
We can also create an equation from scratch if we know the parent nuclides and the type of decay. For example, what will be the product if selenium-75 undergoes beta decay? Selenium has an atomic number of 34, so the atomic numbers of our products must add to 34. One of the products is the beta particle, which has an atomic number of -1. Therefore, the atomic number of our other product must be 35. Because beta particles are electrons, they have an atomic mass of 0, which means the mass of our product must be equal to that of selenium. This makes the product bromine, 75.
Now we will take a look at how this relates to nuclear energy. Nuclear energy can be created when a neutron collides with the nucleus of an atom such as uranium or plutonium. This causes several things to happen. The first is that the impact of the collision causes a tiny amount of the atom's mass to be converted into an enormous amount of thermal energy, which is captured by the power plant. The second is that the addition of the neutron causes the atom to become unstable, which makes it split into 2 smaller atoms, plus a few lone neutrons, which can go on to collide with other molecules, causing a chain reaction of fission.
The split of the nucleus happens somewhat randomly, although some combinations are more common than others. For example, uranium-235 often splits into barium-142 and krypton-91, while plutonium-239 can split into xenon-134 and zirconium-103. Many of these products are radioactive isotopes, which will emit radiation as they decay into a more stable form. As pictured here, beta rays are produced from the decay of many of the products. Additionally, uranium and plutonium themselves are radioactive elements and will produce both alpha and gamma rays.
There are benefits and drawbacks to both uranium and plutonium as a source of nuclear energy. Uranium's half-life is around 700 million years, making its alpha decay not particularly dangerous. Plutonium, on the other hand, has a much shorter half-life of only 24,000 years, meaning it decays at a much faster rate, making it more dangerous. Additionally, plutonium can more easily become airborne, entering living organisms through the lungs and giving the normally harmless alpha particles direct access to the body's cells, where it can do serious damage.
Another factor to consider is the radiation produced by the products of fission. On average, the products of uranium produce more beta radiation than those of plutonium. And at present, we do not have a safe and cost-effective way of disposing of these radioactive products. Methods from burying them in the ground to launching them into space have been proposed, and while each of them has their benefits, they also come with risks. For example, there is only a finite amount of ground on Earth in which to bury radioactive material, and it could become a serious biological hazard in the event of an earthquake. Space disposal would effectively solve this problem, but if something went wrong with the launch, radioactive material would rain down across the Earth.
However, even with all this risk, nuclear energy is still one of the most efficient forms of energy production available to us today, and is one of the only viable replacements for our non-renewable sources of energy, coal and oil. As we continue to deplete our resources, nuclear energy may soon be the only option available to us, at which point more effort will be put toward making it safer for both our health and the environment's.
So, is nuclear energy sustainable? At present, no, but it will be soon, because we will be left with no other choice but to make it so.